two experiments. The video is coupled into one because there is modulation as well as demodulation on the same kit. So we have preferred to record a single video for these two experiments. So today we are going to perform pulse modulation and demodulation, right? As you know, some of the basic things about modulation. In case of modulation, as I tell you on each turn, that in case of modulation, we change the characteristic of the carrier signal with respect to instantaneous values of our message signal. This is a basic thing that we know from definition of modulation, right? In case of amplitude modulation, or if we consider frequency modulation, whatever experiment we have done, we have taken the carrier also of sinusoidal nature, right? The carrier was also a high frequency sinusoidal signal, cos omega ct or sin omega ct, anything we can take. Okay, so in all those modulation schemes, analog modulation schemes that we used to categorize them as, right? We have used sinusoidal as a carrier signal, right? But in case of pulse modulation scheme, we use a pulse signal as our carrier signal. So we are having high frequency pulsating signal, a pulse signal that is having two values, either 0 or some voltage, 5 volt or 2 volt or 3 volt as per the generation. And it is having a frequency that is high frequency signal, because carrier is usually of high frequency signal as compared to the our message signal or data signal, right? So first difference that we need to note here is, in case of this pulse analog modulation, because pulse modulation can be of two types, analog as well as a digital format. You will come to read in detail, or when these topics will be taught in your theory classes. But as of now, you can understand from basics that pulse modulation, first thing you need to note is that the carrier signal is of pulsating nature. So pulse signal is getting used as a carrier signal that is a high frequency signal. When I'll share the link, you will watch the video, you will come to know that on the kit we are having various options for carrier signal. We are having 8 kilohertz option, 16, 32 kilohertz option, 64 kilohertz option for carrier signal, right? As I always tell all of you that in a laboratory environment, when we are performing these experiment on a kit, so that kit is a prototype kit. Our main purpose is to illustrate the basic concept as well as the process, how these things happen in industries or wherever they are being used for communication purpose. So basic concept, how we are using all these communication mediums or communication technologies, that you need to understand, and that is our purpose. So we need to generate data as well as the carrier signal on the kit only, because we don't have the data to send. Because in real scenario, when someone is communicating, then he or she is having some data or some information that he or she wants to communicate. Okay, so in this case, the prototype thing, we need to have a block for generation of our message signal also. So you will see that on this kit, on the kit that we are using for this pulse modulation, we are having a block as function generator. Unfortunately, that block is not working on the kit, so we have used another function generator, a separate function generator, to take our message signal. So we have taken our message signal, a sinusoidal signal of 1 kilohertz as our message signal, right? So in pulse modulation, the carrier signal is of pulsating nature. It doesn't mean that our message signal is of pulsating nature or any other thing. Our message signal can be anything. As similar to our amplitude modulation or frequency modulation, message can be anything. It can have any amplitude, it can have any frequency, right? It is of continuous time a sinusoidal signal. So here also we are taking message signal as a sinusoidal signal of 1 kilohertz, right? So this much we have understood, that in case of pulse modulation, we are using pulse signal as a carrier signal, and message signal can be anything, any continuous time signal or sinusoidal signal, right? Okay, as I was telling all of you that in pulse modulation also there are two kinds of modulation. One is a pulse analog modulation, in which we are having analog signal. That it means that in case of pulse modulation scheme, if we are using a pulse signal as a carrier signal, and the basic principle or mathematical calculation or anything, if you have noticed from your first classes, then we just generally multiply this carrier signal with message signal, right? So if you are multiplying any sinusoidal signal or message signal with a pulse signal, so you can comment that, or you can think of that, anyhow we are sampling that particular continuous time signal by multiplying with this pulse signal. If you are multiplying this pulse signal, high frequency pulse signal, with any sinusoidal signal, it means that the place where the value of this pulse signal is 5 volt or some voltage, then that particular value will be taken from that message signal, and the places where this value of this pulse signal is 0, that particular information is not we are taking. At that point, the amplitude we are going to take is 0. It means that from this particular illustration, or from this particular statement, you can conclude that the one more difference from the continuous time, the AM or FM modulation scheme and this pulse modulation scheme, is that in case of all those schemes, amplitude modulation as well as in frequency modulation or phase modulation or SSP or DSP, we used to transmit the whole signal, all the instantaneous values, whole signal, whole information. But in case of pulse modulation, we are not sending the whole information, but somehow we are taking sufficient samples of the signal, of our message signal, and we are sending that. And that samples need to be sufficient. As you remember from your first experiment, sampling and reconstruction, there is some condition like Nyquist criteria and other criteria, so that if you are sampling any signal, then you need to take sufficient number of samples, that is by Nyquist criteria at least twice of the frequency of your message signal or more than that, then you can completely reconstruct that signal at the receiver end. So if we are taking sufficient sample, it means that one difference you can say from this pulse modulation and your another analog modulation scheme, continuous time sinusoidal systems, you can directly say that in this case, pulse modulation scheme, we are not sending the whole information. It means that we are sending sufficient number of samples or information of our message signal, and by some means, by synchronization, by using some pulses, by using some methods, we are retrieving that particular signal at the receiver, and we are retrieving back the whole signal, the continuous time whole signal at the receiver end. So this is one difference. First difference is we are using pulse carrier signal. Second difference is we are not sending the whole information of the signal. We are not sending all instantaneous values or whole signal in this case, but we are sending some samples, right? So in this case, we are sending some samples. But when we are taking samples of any continuous time signal, so we are not restricting the amplitude of that signal. The amplitude of that signal, message signal, can be any real values, positive, negative, or any real values it can take when we are talking about pulse analog modulation, right? So it means that the amplitude can be any. But what if we divide this amplitude to some quantized levels and we send only those quantized level values and or the encoded values of those quantized level? Then we switch to pulse digital modulation, right? So I was telling all of you that pulse modulation is of two types: pulse analog modulation and digital modulation. In case of pulse analog modulation, the amplitude of the message signal can be any real values. It can be of any real values. If we sample or if we divide it into levels, quantized levels, and allot them some code, and only those values that fall on that particular level or in between that level is going to get transmitted. In that case, we are limiting the amplitude of the message signal also. In that case, we can say that it is pulse digital modulation scheme. If you have read about all these schemes, so in pulse analog modulation scheme, we are having pulse amplitude modulation, pulse position modulation, and pulse width modulation, right? So today we are going to deal with this analog modulation scheme. You will come to know about the digital schemes also. We are having some experiments related to those digital pulse digital schemes also, like PCM systems, pulse code modulation, like delta modulation, adaptive delta modulation. There are so many digital schemes, pulse digital schemes also. So we are having some experiment to perform on digital schemes also, right? So we will perform it on the next turns also, hopefully. So today we are going to deal with pulse analog modulation schemes. And the schemes are three: the pulse amplitude modulation, pulse width modulation, and pulse position modulation, right? So we are having these three modulation as well as demodulation of these three, right? So we are having pulse amplitude, pulse width, and pulse position. Okay. Sorry. So As far as modulation is concerned, the pulse amplitude modulation is concerned, you can easily see that if you multiply the signal, the message signal with your this carrier signal, the high frequency pulsating signal, then the samples of that particular message signal, a continuous time sinusoidal signal that we are taking here as a 1 kilohertz signal as our message signal, it is going to get sampled at the rate of this 8 kilohertz or 16 kilohertz, whatever with the frequency of our carrier signal, right? It means after multiplication of these two, we are going to get the pulse amplitude modulation. But when we multiply these two, as far as the top of this pulse signal is concerned, wherever its value is 5 volt, it is flat. But when we multiply it by sinusoidal signal, whatever be the shape of that particular sinusoidal signal, either it be increasing or decreasing, or it is at the global maxima or global minima, whatever be the shape over there, it will get attached to that particular our pulse signal, right? It is very much easy to imagine that because you are multiplying these two, so the amplitude level will be, and this type of sampling is called as natural sampling. So there are two types of methods that we use to generate pulse amplitude modulation schemes. So we are having this natural sampling as well as the uh, flat top sampling. In case of flat top sampling, we used to make this top as a flat with we use some sample and hold and other techniques to make that top flat. Okay, so in the kit the flat top pin is not working, so I tried to illustrate that particular thing also, but unfortunately the pin was not working, so I couldn't. But at least you must know that the pulse amplitude modulation signal can be generated just by multiplying a pulse high frequency pulse signal with our message signal, sinusoidal or any continuous time message signal, and it is just get sampled, right? So we have shown the natural sampling. You can easily see that the waveform after multiplication would be having sampled output, but the nature or envelope of that waveform, the pulse signal, is going to be looking like a sinusoidal signal, right? And after we know that our message signal is a low frequency signal, so as far as demodulation is concerned, we just use low pass filter and demodulate it, right? So this is our pulse amplitude modulation, in which the information or instantaneous value of our message signal is stored or is stored in the amplitude of our carrier signal. As you can remember from DSB AM modulation, the instantaneous value or the information of our message signal is stored in amplitude of our carrier signal, right? In frequency modulation, we saw that the information or instantaneous value of our message signal is stored in frequency variation of our carrier signal. So we name it as a frequency modulation. In a very similar way, if we are anyhow able to include the information of our message signal in the width of our pulse signal or in position of our pulse signal, it means that when the signal our message signal is having amplitude positive high amplitude plus AM, you can say, or minus AM. At that point, the position of the signals, the pulse signals, is varied accordingly to that particular amplitude, right? If the amplitude is high, it means the waves are having positioned closely. If it is getting low, then at that point of time, the position of the pulses are separated in that way. In that case, we can generate the pulse position modulation, or if we connect these amplitude values with the width of our pulse signal, it means that when amplitude is lesser, the width of our pulse signal would be lesser in that case. And if the amplitude is high, then in that case, the width of our pulse signal is higher. It means that the information of amplitude or instantaneous value, the sampled output that we are getting, is getting stored in width of our carrier signal, the pulse signal. So it means that width of the carrier signal is going to change, or it is uh, dynamically changing with respect to the instantaneous value of our message signal. In that case, you can say easily that we are performing pulse width modulation. So in all these three schemes, pulse analog modulation schemes, in which we are going to perform pulse amplitude modulation and pulse width and position modulation, the information or instantaneous value, or if I say precisely, then the sampling is done in each of the cases. We are taking samples of the particular message signal. So it is confirmed that we are not sending the whole signal, whole information, whole message in case of pulse modulation, but we are sending the sampled output. So sufficient number of samples is needed. Okay, sufficient number of samples are to be there in order to send the whole information and retrieve that. As far as demodulation of all these three schemes are concerned, since we are having this message signal as a low frequency signal, so we can use any of the filter that can suppress the high frequency and can let pass the low frequency. So such operation can be performed by our low pass filter. So we have used the low pass filter at the demodulation. We just give output of this uh, pulse amplitude modulator and pulse position modulator and pulse width modulator one by one to the low pass filter, and we have retrieved our message signal back, and I have illustrated on the DSO that we have retrieved our message signal back completely. Okay, so the thing is that in real scenario we are not doing it on the same place, because if we are communicating at the same place, so there is no need of communication system. The transmitter and receiver must be at farther place. That's why there is purpose of some communication, right? We use transmitter and receiver, the transmitting antenna, receiving antenna, as well as the so many electronic systems and components, analog components that can perform all these processes at the transmitter end and at the receiver end, and both are at the farther place. But as we are performing it on the same kit, and the kit is a prototype kit, so we want to illustrate that process. So we have assumed that whatever we are transmitting from the transmitter, we are receiving at the same place, and we have connected it using a wired mode just to illustrate. But in real scenario it is not going to happen. In real scenario these two things are at the farther place. Whatever be the output that you are getting after PAM, pulse amplitude modulation or pulse position modulation or pulse width modulation, you are going to transmit that signal through transmitting antenna into the air, and at the receiving end the receiving antenna can receive that signal and demodulate that using some noise removal techniques and some smoothing techniques. After that, using a low pass filter, it can directly demodulate the signal and can see whatever with the information the transmitter was willing to transmit, right? So this is the process in real scenario. So you can uh, watch the video. I'm going to share the link so that you can complete the video. So complete the video. I hope it will be of not more than 35 minutes. So you can complete the video. I'm going to share the link, and if there is any query, any confusion, then you can ask. Okay, so I have illustrated all the three, the amplitude modulation, pulse amplitude, pulse position, and pulse width modulation, as well as demodulation. So this 35-minute video is of for two of the experiments. So we have completed already 5 experiment till your previous laboratory class. So I have created an assignment also, so that you can submit all the reports, combine it into one file in PDF format, and submit it with a name of the file with your name and roll number, right? And submit it before the due date. Okay, so you can watch the video. If you are having any query, then you can ask, right? And we will meet after 35 or 40 minutes. I'll take your queries as well as attendance. I hope you all will watch the video completely and you will learn something. Okay, so do let me know if the link is working fine, and we will meet after 30, 35 or 40 minutes, right? In order to take your queries, I'll take your queries if any, and I'll take your attendance also at that time. Meanwhile, if you are having any confusion, then you can raise your hand, you can unmute yourself and ask, you can comment on the chat box and ask your query. Okay, so just go and watch the link, and we'll meet after 35 40 minutes. I'll take your queries, and do let me know if the link is working fine. Okay.